As we move into Chapter 4, in Section 1, we're introduced to exponential functions. Now, we are moving away from our traditional algebraic functions where we were adding, subtracting, multiplying, dividing, focusing on powers and roots, and we're moving towards what we call transcendental functions. They transcend our algebraic functions. With transcendental functions, now our variable is in the exponent of the function, not the base. And transcendental functions, specifically exponential functions, show patterns of growth and decay. So you have an exponential increase or an exponential decrease. The inverse of my exponential function is a logarithmic function. In fact, we define logarithms as the answer to the logarithm is the exponent that causes a value to occur. All right, we define exponential function as a function where the variable is in the exponent. So we need to talk about what is the exponent, what is the base. If I have 2 cubed equals 8, I have a base of 2 raised to an exponent of 3, and that is equal to the argument 8. So I have three terms here that I want to focus on. A base raised to an exponent yields an argument. What is our definition of our exponential function? Well, here we have it. And this is the definition that we will refer back to throughout this unit. An exponential function with base a is equal to f of x, my function notation, is equal to a to the x, where my variable is in the exponent. Now I have some limitations on a, where x and a are real numbers, and notice that I define a. A has to be greater than 0, so positive, and not equal to 1. Now let's think about why this is. A needs to be greater than 0, A can't be equal to 1. I started with the wrong one. A can't be equal to 1 because 1 raised to any power is just 1. It's what we call a constant function. It doesn't show growth or decay, and by definition, our exponential functions should show growth and decay. A can't be negative and can't be 0. It has to be greater than 0, but because otherwise it might end up being imaginary. For example, if I had negative 3 to the 1/2 power, that's the same thing as the square root of negative 3, and that's an imaginary number. So that base can't be negative, or it could also end up being undefined. If it's 0, for example, 0 to the negative 2, if I put that negative tells me to take my base to the denominator. 1 over 0, anything over 0 is undefined. So we restrict our base, our value of a, to positive values that are not 1. Positive values other than 1. Okay, the rest of this page talks about finding a pattern. I want you guys to do me a favor, and we are going to start here at 2 to the first and move down, and then we're going to do 3 to the first and move down, and then 4 to the first and move down. I want you to pause your video, and I want you to figure these out. Now, if you need to use your calculator, that's okay. My exponent button is right here. For example, 2 to the 5th, I key in 2, I hit the exponent button, and then the 5 to get 2 to the 5th is 32. So pause your video, and when you come back, I want you to have started for each of the bases, 2, 3, and 4, at the first exponent and move down to the 5th power. Okay, so here we go. I did mine from 2 to the 1st to 2 to the 5th, 3 to the 1st down to 3 to the 5th, and the base 4 down to 4 to the 5th. Hopefully you started noticing a pattern. If I'm doing my base 2's, every time my exponent increases by 1, then my answer is multiplied by 2. So 2 to the 1st is 2, 2 squared is 4, 2 cubed is 8, etc., etc. Same thing for base 3. Each time I increase my exponent, I'm multiplying again by 3. So 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. Same process for 4s. Base 4, each time my exponent increases by again, my argument gets multiplied by another 4. What about anything to the 0 power? Well, let's work backwards. If I start down here at 2 to the 5th and I move back up my list to 2 to the 4th, my argument, instead of being multiplied, since I'm going backwards, is now divided by a factor of 2. So 32 divided by 2 is 16, divided by 2 is 8, divided by 2 is 4, divided by 2 is 2. If I follow that pattern, this one, 2 to the 0, is going to be 2 divided by 2. Well, 2 divided by 2 is 1. Let's look at base 3. If I start down here at 243, I divide by 3 to get 81, divide by 3 to get 27, divide by 3 to get 9, divide by 3 to get 3. 3 divided by 3 is 1. I'm sure you can guess what 4 to the 0 power is. Anything to the 0 power is 1. Because I'm always, if I'm subtracting in my exponent, I'm dividing in my argument. Just like if I were adding in my exponent, I would be multiplying in my argument. Let's follow this pattern up through our base 2's. So we've been, as we move up, dividing by 2. We did 2 divided by 2 is 1. Well, what is 1 divided by 2? 1 divided by 2 is 1/2. What's 1/2 divided by 2? Well, a half divided by 2 is the same thing as times a half, which would be a fourth. And a fourth divided by 2 would be times a half, so that's an eighth. And what do you think this one's going to be? Hopefully you said a 16th. And now I want to stop and think for a second and notice that as we move away from 2 to the 0, we have a pattern forming again. 2 squared is 4. 2 to the negative 2 is 1 over 4. 2 to the 4th is 16. 2 to the negative 4 is 1 over 16. 2 to the 5th is 32. That means that 2 to the negative 5th is 1 over 32. That negative in the exponent tells me to take the reciprocal of the base. Now that you can recognize this pattern, hopefully you can fill in these values for base 3 and base 4. For example, 3 squared is 9, so I know that 3 to the negative 2 is 1 over 9. Over here at base 4, 4 to the 4th is 256, so I automatically know that 4 to the negative 4th is 1 over 256. Again, I'm going to pause my video, fill in the rest of this page while you fill in yours, and then you unpause yours to come back. All right, so there's our pattern of exponents. That leads us right into some rules for exponents so that we can remember how to apply this no matter what our base is. Because exponential functions and logarithmic functions are inverses, once we learn our rules for exponents, they're going to carry us forward into logarithms so that we know our rules for logarithms pretty much as well. First rule for exponents, 0 exponent. Anything raised to the 0 power is 1. In general terms, this looks like m to the 0 is 1, where m can be any number. We just did 3 to the 0 is 1. I know that 5 to the 0 is 1. If I put negative 10 in parentheses to the 0 power, that is also 1. My second rule for exponents is for negative exponents. To do a negative exponent, I take the reciprocal of the base. So, for example, m to the negative 1 is 1 over m. That's my general case. So over here, I've got my general case for my rules. Some examples of this one. We did 2 to the negative 3 would be 1 over 8 because 2 cubed is 8. we did 3 to the negative 4, and we figured out that that would be 1 over 81 because 3 to the 4th is 81. What if I gave you 2/3 to the negative 2? Well, I have to flip this and take the reciprocal of the base. So the base is 3/2 now. I still have an exponent. My exponent is no longer negative, now it's positive, but I still need to square both the numerator and the denominator. So the exponent doesn't go away when I take the reciprocal, it just becomes positive. Rational exponents. A rational exponent is an exponent that looks like a fraction. When I have a rational exponent, I'm going to take the root. I use the denominator of the exponent as the index of my radical, and I use the numerator as the power. For example, if I have 27 to the 2/3 power, that 2/3 is a rational exponent. That tells me immediately when I see that I have a rational exponent that I have a radical, and this 27 is the argument, the radicand underneath my radical. My numerator is the index. No, excuse me. My numerator is the power. My denominator is the index. It's the index. There we go. So if I'm taking the third, so the 2/3, that 3 gives me the index right there. So I'm doing the cube root of, and then my numerator is the power. Once I've taken that root, I want to square the result. Now, when I'm dealing with real numbers, not imaginary numbers, the order here is a little irrelevant. You're going to get the same result either way. But instead of squaring 27, that gets huge. I got to figure out what to do with that. I'm going to stay as small as possible. I'm going to take the cube root of 27. What value times itself 3 times gives me 27? Well, that's 3. And then I still have to square that 3. 3 squared is 9. Okay, so those are my general rules for exponents. Let's do a little practice with these rules. We have 3 different practice problems, and for each of our 3 setups, each of our 3 exponential functions, we have 3 different practices where we're plugging in different values for x. For f of x, I have the exponential function f of x equals 4 to the x. I know it's an exponential function because the variable is the exponent. So each of these is giving me a new value to plug in for that x. Well, f of 3 would just be 4 cubed, and we learned in the last page that that is 64, or you know how to use your calculator for that. F of negative 2 means I have 4 to the negative 2. Well, that negative exponent tells me to take the reciprocal of the base. I still need to square that 4, so I have 1 over 16, also was on our pattern on the last page. And finally, I have a rational exponent, 4 to the 3/2. Well, rational exponents mean I have a radical. I need to take the root. The 4 is the radicand. My index is that denominator. It's just the square root, so I don't need to write anything there. But then I'm going to need to cube that. The square root of 4 is 2, and 2 cubed is 8. All right, let's switch to g of x, where g of x is 5 to the 2 minus x power. Again, it's an exponential function because my variable is in the exponent. Where I'm finding g of 3, I have 5 to the 2 minus 3, which simplifies 5 to the negative 1. Well, that negative exponent tells me to take the reciprocal of the base. For g of negative 2, I have 5 to the 2 minus 2 minus x. 2 minus a negative 2 becomes 2 plus 2. That starts as 2 minus a negative 2, which becomes 2 plus 2. So I have 5 to the 4th power. Well, we didn't do base 5, but I did show you how to do this on your calculator. If you can't work that out in your head, that's fine. You want to plug in your base, use your exponent button, that little house top, and we have the 4th as our exponent, and we get 625. That is the argument. Base raised to an exponent yields an argument. Okay, let's do number 3, where h of x is 1/3 to the x power. H of negative 2 means I have 1/3 to the negative 2, and that negative in my exponent tells me to take the reciprocal of my base. Well, when I flip this, 3 over 1 is the same thing as 3. I still need to square that. The exponent doesn't go away. I just took care of the negative by taking the reciprocal. And finally on this page, h of 3 would be 1/3 to the third power, or 1/3 cubed. 1 cubed is 1, 3 cubed is 27. Always when I get a fraction, I want to simplify, put it in lowest terms. I do not change it to a decimal unless I'm told to. Typically, if I change to decimal too often, I end up having to round that off, and then I have an approximate value, not an exact answer. What about graphing exponential functions? Well, graphing exponential functions are going to follow our pattern of transformations that we learned in the last unit, but we need to identify what the shape of our graph is going to be. We did introduce the parent exponential function when we introduced all of our families of functions, but we didn't focus on our exponential function shape. F of x equals a to the x for all a greater than 0 and not equal to 1. Remember, that is our definition for an exponential function. Notice that a is the base of my exponent. It is not the same thing as the domain or the range for my graph. My exponential function has a domain of all real numbers, just like my polynomial functions did, which means it starts all real numbers for the parent function. It's going to be all real numbers for any exponential family of functions. The range, however, is going to be limited by a horizontal asymptote. The range is limited by a horizontal asymptote. Now that means that our range is going to change whenever I have a horizontal shift up or down. Vertical shift up or down. That horizontal asymptote is going to move. So where does my vertical shift show up? It shows up at that plus k. That's that vertical shift that is going to move my asymptote, that horizontal line, up or down and shift my graph up or down. The pattern of transformations is the exact same as it was for polynomial functions. H is still my horizontal shift. It's attached to the x just like it always has been, and it starts out horizontal. I'm sorry, my pen is cutting out. Horizontal shift. It starts out as x minus h, so it still goes the opposite direction from what we kind of expect it to. And notice that if we have negatives, we reflect. If we have a negative out in front, we reflect across the x-axis. So we would flip it upside down. Okay, we're going to start with base 3 as our parent function. When you're graphing exponential functions, you just pick a base. It has to be positive and it cannot be 1. Remember, there's our restrictions for our base. Have to be positive, not 1. And you use it to graph the parent function. Now for our examples here, I chose 3 as my base. I could have chosen 2, I could have chosen 5, I could have chosen any positive value, not 1. But I chose 3. So all of these functions are going to be base 3. Remember that my domain is all real numbers, we were told, for my exponential family of functions, so I can use any x value I want. I'm going to tell you right off the bat that we start with kind of a basic 5 functions to plug in. -2, -1, 0, 1, and 2. Those are my 5 basic values that I plug into x to get out y. Let me go ahead and kind of define a little bit of space for each of these. F of x is 3 to the x. So here I have 3 to the -2. Well, negative exponent tells me to take the reciprocal. That gives me -2 1/2 as that ordered pair. If I have 3 to the -1, I have 1/3. So that ordered pair is -1 1/3. Anything to the 0 power is 1. 3 to the first is 3, and 3 squared is 9. Look at that. That's getting bigger and bigger and bigger. These fractions, if I worked my way back up the row, would become smaller and smaller and smaller. They are getting closer and closer and closer to the value 0. So let's graph our exponential function base 3 here, where we have x is 0, y is 1. That's my y-intercept. Where we had x is 1, y was at 3, 1, 2, 3. where we had x is 2, y is way up here at 9. So we've got our exponential increase going zoom. It's not going straight up, but it's going up really steeply. Where x was -1, we were at 1/3, and where x was -2, we were at 1/9. We're getting tinier and tinier successive fractions that get closer and closer to 0, which is my horizontal asymptote. We know horizontal and vertical asymptotes because of our rational functions from 3.5. Okay, so we have a horizontal asymptote at 0 for our parent function. Horizontal asymptote at y equals 0. And that gives us the restriction on our range. Our range is from 0 to positive infinity, and 0 is not inclusive because that value 0, it never gets there. These fractions are just going to get smaller and smaller and smaller. Okay, this is my parent function that I'm going to transform. So I'm going to go ahead and I'm going to sketch this parent function on each of these three sets of axes. My parent function goes through the y-intercept 0, 1, and it has a horizontal asymptote at the x-axis at y equals 0. And those are the things that are going to be consistent all the way across. So let's go ahead and sketch our parent function. Base 3 is fairly steep. Base 5 would be even steeper because it would be pair 5 to the 1 would be 5, 5 squared would be 25. 1/2 is going to be a little less steep than 3, but they all have the same general shape. All right, g of x, 3 to the x plus 2. That is my horizontal shift. Since it's x plus 2, I have shifted it, taken my function and shifted it to the left 2 units because h is a -2. So I'm going to take my y-intercept, this point that starts out at 0, 1. That's my y-intercept. I'm going to shift it to the left 2 places. So it goes over 1, over 2. My horizontal asymptote is not going to change because I did not have a shift up or down. So this point 0, 1 is now at -2, 1. My horizontal asymptote has not changed. My domain is all real numbers. If it starts all real numbers, it stays all real numbers. My range is still not inclusive, so parentheses 0 to infinity because I didn't shift up or down. Let's do h of x is 3 to the x plus 2. This plus 2 is tacked on at the end, so that is a vertical shift. This graph is going to shift up 2 units. So I'm going to take this point 0, 1 and I'm going to go up 1, 2. So now it's at 0, 3. And I'm going to take my horizontal asymptote from 0, y equals 0, and now it goes up 2, so it's at y equals 2. So when I have a vertical shift, I do have to shift my y asymptote, or my horizontal asymptote. Horizontal asymptote is now at y equals 2. When I sketch that graph, it follows the exact same curve, it's just shifted up. My domain is still all real numbers. My range now, instead of from 0 to infinity, is now 2 to infinity because my horizontal asymptote is at 2. The last example that we're going to do of x is equal to a -3 to the x. Well, remember that negative out in front causes my graph to reflect across the x-axis. So this point 0, 1 flips down to become 0, -1. My horizontal asymptote has not changed. I just have a reflection. My domain is still all real numbers. If it starts all real numbers, it stays all real numbers. My range, instead of having a lower limit, now has an upper limit. So my range is from -infinity up to 0 this time. One other concept that 4.1 introduces is the natural base. We're going to use the natural base when we calculate compound interest. we're going to introduce two different compound interest formulas here. A general compound interest formula and a compounded continuously interest formula. You don't have to stress about memorizing either one of these formulas. They will be available to you to use on your exam. These are good formulas to know. They're very common formulas. We're going to talk about how we find those, but this E is an irrational constant and it's our natural base. Let's look back up here at the beginning of this page. Many real-life situations can be described using exponential functions. They track rates of exponential growth, like with people, populations, animals, microbe populations, growth of epidemics, like our pandemic. You've seen a lot of graphs. This is summer of 2020 right now. You see lots of graphs with the COVID-19 growth rates. Radioactive decay. So there's our exponential decay, where you start talking about half-lives and things like that. Other changes that involve rapid increase and decrease can be tracked using our logarithmic and exponential functions. Sometimes these changes are modeled using what we call the natural base. Now, our natural base is the irrational number E. An irrational constant, one you're more familiar with, is pi. Usually we talk about pi as being worth 3.14, but that's an approximation. Pi is an irrational constant, which means it has a decimal that continues on and on forever. On your calculator, I want you to find the button for pi. You see it's right here. So if I just press pi and hit enter, I've got 3.14, and then I get decimal until I run out of screen. My decimal did not end here, I just ran out of room. So my calculator has rounded it off here at the end of my screen. E is another irrational constant like pi. Now we're going to find E on your calculator. It is right above natural log, ln. The second function of natural log is e to the x. So I want you to, on your calculator, do e to the first power. So I'm just going to do second function natural log. That brings up e to the exponent, and I'm going to plug in a 1 there because I have to have it, you know, to something, and 1 gives me anything to the first power is itself. So e to the first power, this is my rounded off value for e, my irrational constant e, which is the base of my natural log. If I round that to 2 decimal places, it's approximately 2.72. So the value of e to 2 decimal places is 2.72, just like the value of pi to 2 decimal places is 3.14. That's the answer to this question here. What are we more familiar with? We're more familiar with pi, and we round it to 3.14. I tend to get ahead of myself. Okay, why do we care? Why does this matter? Well, we use base E in some application problems. For example, the cost of a family's health insurance X years after 2000 can be modeled by this function, g of x equals 6,875 times e to the 0.077x power. What was the cost for health insurance in 2011? Well, if x is the number of years after 2000 and we're interested in 2011, then x is equal to 11. Now this is just a calculator math problem. It's kind of plug and chug. We've got g of x. In this case, we're interested in g of 11, and we plug in that 11 for x. So we've got order of operations 6,875 times e to the exponent 0.077 times 11, because x is 11. Now, we're going to have an approximate answer, and it's going to be in money because we're looking at cost. So we're going to round it to the nearest penny. You need to be able to do order of operations correctly in your calculator for this problem. We start with parentheses and exponents first. So we do e to the power first, and then we're going to multiply that by 6,875. So I push second natural log to bring up e to the, and then inside that parentheses, I plug in my exponent, 0.077 times 11. I'm going to go ahead and close my parentheses there and hit enter. That is e to the power of, and then I'm going to multiply that times 6,875. Do not round in the middle of a problem. Leave it all right there. Just push times, and see it says that last answer times 6,875 is equals, and there is your result. You want to round it to the nearest penny. So in 2011, the cost of health care for a family was $1,600. Oh, no, for a year, $16,036.89. That's our approximation rounded off to the nearest penny. Well, according to this model, what's the cost this year in 2020? Well, in 2020, x would be 20. So I'm finding g of 20 is equal to the same function, the same model, but this time my exponent is going to be different. I want you to plug that into your calculator and round that to the nearest penny. And that's the value that you should get. Now, let's go ahead and work on some compound interest problems. Compound interest problems, whether you're just using the generally compounded interest formula or the compounded continuously calculation, has variables in common. A is the amount that you have at the end of the investment. So we're looking at investing money, and interest is being compounded. The amount at the end of the investment is the principal plus the interest, and that's what you're solving for both of these equations. P is the principal, or how much you have to invest. R is the rate of return. So if your interest rate is going to be R, you always use it as a decimal. You'll be given an interest rate as a percent, but you want to use it as a decimal. Then N is the number of times compounded in a year. N is for number, so it's the number of times compounded per year. So if you're told that your interest is compounded quarterly, N is 4. If you're told it's compounded monthly, N is going to be 12 because there's 12 months in a year. We follow the banker's rule, so if you're told it's compounded daily, N would be 360 for both of these locations. Notice that there is not an N in our compounded continuously formula because we don't have a number of times compounded. It's always being compounded. Finally, T is the term of the investment or time of the investment, and it's going to be in years unless you're told otherwise. And for our purposes this semester, it's always going to be in years. So just be aware, FYI, if you were told 18 months, T is not 18. 18 months is a year and a half, so T would be 1.5. Okay, let's do our sample problem. You're given $10,000 by Aunt Gerda, and you decide to invest it at an annual rate of 5.5%. How much money is going to be in the account after 5 years if it is compounded monthly? Well, compounded monthly is our general compounding formula. So we're going to be plugging into this first calculation. We're finding A, the amount of money in the account. For P, the principal, $10,000, because that's how much I'm investing. 1 plus R is our rate, but we need to write it as a decimal. My rate is given as 5.5%. Change that percent to a decimal by moving that decimal place 2 places to the left, as this is 5.5 out of 100 or divided by 100. So that's 0.055. Over N, where N is the number of times compounded per year, I'm told it's compounded monthly and there are 12 months in a year. This is all raised to the NT power. Well, N we just said is 12. T is the time we're leaving it invested, in this case 5 years. Okay, so let's plug this into your calculator and see what we get. When I work on this, I'm going to use order of operations starting inside my parentheses first with this ratio. So I'm going to start with a ratio 0.055 divided by 12. So into my calculator, I key 0.055 divided by 12, enter, and I get this decimal. I need to add 1 to that. So plus 1, enter. And now this value is what is inside my parentheses. I am not going to round that off. I'm going to leave it just like it is. I need to raise that to this exponent because order of operations says parentheses and exponents first. So I need to raise this value to an exponent. Since I'm raising this value that's already here, I just push my exponent button and it uses that value, not rounded off. Now my exponent is 12 times 5. If I know 12 times 5 is 60, I can just key in 60. However, if I don't know that 12 times 5 is 60, I have to use parentheses around that multiplication problem. If I don't put that inside parentheses, it would take my answer, raise it to the 12th power, get that answer, and then multiply it times 5. That's not correct. We need our exponent to be this 12 times 5. So I key it in like this, push enter, and this is the value that I need to multiply times 10,000. So after 5 years, my $10,000 that Aunt Gerda has given me has become $13,157, and I round it to the nearest penny and 4 cents. So that comes out to be approximately $13,157.04. Out of that, how much is interest? Well, I invested $10,000, so that $3,157.04 is the interest I earned. The next problem says, well, what if it was just compounded quarterly? What if it wasn't compounded monthly, but it was compounded quarterly? Well, in that case, n is going to be 4, but otherwise, I do the same calculation. So I have 10,000 times the quantity 1 plus 0.055 over 4 this time to the 4 times 5 power, because n goes in both of those places. If you plug that into your calculator correctly, you get just a little less interest because it's not being compounded quite as frequently. Now our last problem here says, okay, well, what if we have our 10,000 at 5.5%, but it's compounded continuously? This time we're using our other calculation. A equals P times e to the RT power. My principal is still that 10,000. Now I have that constant e, irrational constant e, raised to the RT power, where t is 5 years. So r is my rate turned into a decimal, t is the years. Now, order of operations, I'm going to do e to that exponent first. So let's bring back our calculator. E is the second function above natural log, so there's my e. My exponent is 0.055 times 5, enter, and that is the amount I'm going to multiply times my 10,000. You can see that when it's compounded continuously, I get a little more interest than even compounded monthly or compounded weekly or compounded daily. So I have $13,165.31 approximately, because I've rounded it to the nearest penny.